Welcome back to the second introductory lecture on proof techniques. In this fifth segment, we're going to introduce two new proof techniques. And you might wonder why we need even more proof techniques. Well, let me remind you that when we talked about direct and indirect proofs, these only applied to theorems of the form P implies Q, in other words, conditionals. But not every theorem is stated as a conditional. In particular, some theorems are stated as equivalences, like P if and only if Q. So we need new proof techniques to handle these kind of theorems. Now, fortunately, the technique we're going to discuss now is just a slight variation on the previous one, so it's really not much new. Now, how would you prove the theorem P if and only if Q? Well, that's when you need to remember that we studied a logical equivalence earlier of the form P if and only if Q is logically equivalent to P implies Q and Q implies P. In particular, what it means is that to prove this theorem, you are completely entitled to prove this equivalent theorem. And this theorem is nothing but the conjunction of two conditionals. And that is the key. In other words, if you want to prove a theorem of the form P if and only if or equivalent to Q, you can complete this proof by breaking it down into two subproofs. One proving that P implies Q is true, which is the first half of this conjunction, and the second subproof for Q implies P. And of course, for these conditional proofs, you can use any of the techniques we have discussed so far. So the key here is to realize that a biconditional is simply the conjunction of two conditionals. And these are called equivalence proofs because the theorem states the equivalence between P and Q. In other words, P if and only if Q. So to illustrate this new proof technique, I will let you prove theorem number 2 in this lecture, namely for every positive integer n is odd if and only if n squared is odd. So my hint here is, to prove this theorem, first of all you must do a universal generalization proof, but the core of the proof will be to prove this equivalence. And this equivalence is proved in two steps. First, you prove the if direction, namely, if n squared is odd, then n is odd. And then the second subproof is the only if direction. In other words, n is odd only if n squared is odd. So please pause the video and complete this proof for yourself. So I hope that this example convinced you that to prove an equivalence, you can simply prove two conditionals. Well, it turns out some theorems are even more complicated than stating an equivalence because they state several equivalences. In fact, some theorems are stated like this. They say proposition P1, proposition P2, ... proposition Pn are all equivalent. And what it means is that P1 is equivalent to P2, P2 is equivalent to P3, ... Pn minus 1 is equivalent to Pn. In other words, it's really stating n minus 1 equivalences. So one way to prove such a theorem is to take these n minus 1 equivalences and to prove each of them as two conditionals. So in conclusion, if you follow this approach, you would end up proving 2 times n minus 1 conditionals. Well, that's all right, but actually there's a much more efficient way of proving such theorems, and here is the trick. Instead of proving 2 times n minus 1 conditionals, it's actually enough to prove n conditionals. And here they are. The first conditional you should prove is that P1 implies P2. Then you prove P2 implies P3. Then P3 implies P4, ... until you reach Pn minus 1 implies Pn. Notice you've just proved n minus 1 propositions. That's half of the workload we just talked about. But of course, all you've proved is that each proposition implies the next proposition in the list. What's missing is proving the conditionals in the other direction. In particular, you never proved that Pn implies Pn minus 1, nor that P3 implies P2 or P2 implies P1. So in other words, we are missing half of the proofs. But the beautiful thing here is that we can complete this proof by adding a single conditional proof, namely that Pn implies P1. And I claim that this will automatically prove the other half of the set of conditionals we needed. And here's why. By proving that Pn implies P1, you're closing the circle to where you started from. And therefore, by transitivity of the conditional, if Pn implies P1, and we already proved that P1 implies P2, then we can infer automatically without doing anything that Pn implies P2. But since Pn implies P2 and we already proved that P2 implies P3, then we can infer right away without any extra work that Pn implies P3. And so on and so forth until we've ended up proving the conditionals, all of the conditionals in the other direction here, from left to right. And this is done using a single additional conditional, namely this one. So this is a pretty smart way of proving theorems of this form. So to illustrate this proof technique, I will let you work on the proof of this theorem on your own. It says, for every positive integer n, the following statements are equivalent, namely n is even, n minus 1 is odd, and n squared is even. So if we successfully proved theorem 3 using the technique we just described, you must have written 3 proofs of conditionals. Namely, you must have proved that P1 implies P2, that P2 implies P3, and finally that P3 implies P1. So you should have written 3 conditional proofs instead of 4 proofs, 4 being equal to 2 times 3 minus 1, 2 times 2 is 4. So in other words, you only saved 1 proof or subproof. But remember that in general, the savings is almost half. Remember, when n gets large, the savings is from 2 times n minus 1 proofs down to just n proofs. So this concludes our segment on 2 types of equivalence proofs.